Okay, so just to round off this series of videos, I suppose you could say, on how to interpret an isokinetic report, we're going to finish with what, for my money at least, are the three least frequently found metrics within the published literature. The first being range of motion, obviously. It's not something that we're going to study. Doesn't mean it doesn't have some value, but it's not something that's going to be published within the literature. And finally then acceleration and deceleration time, which are just above range of motion there. Doesn't mean they don't have their value. Everything on an isokinetic report can be interpreted obviously in one way, shape or form, but these are the three that I would place least emphasis on, arguably, in your written report. So let's start with range of motion. This is fairly obvious. This is determined when you're setting the test up, so you dictate what the range of motion is. The main value that I find in range of motion is in comparison between tests. So we may have set this range of motion here on the right leg at 93.5 and on the left leg at 102.5, and that's fine because this is the range of motion that the movement is going to occur through. But where this becomes interesting is when we compare with other tests. So this is the 360 degrees per second angular velocity. If we just scroll down to the 60 degree per second test, we see that range of motion is now 88.3 and 97.2. Now this is very common. This is very common to see in someone that hasn't had a good familiarization session, or an appropriate familiarization session, I should say. And we usually see a shortened range of motion with a more challenging test. So one that has a lower angular velocity, so 60 degrees per second versus 360 degrees per second. So again, let's just compare that 88.3, 97.2 with the 93.5 and the 102.5. So how I would use this information is as a measure of the quality and the efficacy of the test. Was the participant moving through the full range of motion? Obviously that's going to be more likely with an easier test, i.e. a test at a higher angular velocity, 360 degrees per second. So we can even compare this with the 180 degrees per second test. So just make a mental note of these two digits, and you see not too far off here. So again, this is an easier test. We're talking 93.5. We're talking about less than a degree difference, but we are seeing a far greater difference here with this harder 60 degree per second test. Now you might think, well, what does that matter? But it matters a lot when we think about how we interpret these work values, which is another reason to consider work more of a relevant measurement for a higher angular velocity test with more repetitions, because it is more likely that your participant is going to, say, cheat the test seems harsh, but whether they consciously or unconsciously mean to do it, they may shorten the range of motion with a more challenging test. Doesn't make the work reading any less or more valid, because at the end of the day you're still calculating work for that given range of motion, but it does mean that they haven't moved through the full range of motion that you originally set up when you first were setting up the test. So you haven't got a full measurement of the limb performance throughout their possible range of motion, because they themselves have cut it short. So I would use this along with the coefficient of variance and the max repetition. Let me just highlight that with the coefficient of variance and the max repetition, max work repetition. I always get these two confused. as a hallmark of the quality of the test that was performed. So with a high coefficient of variance, again it varies, but anything over 15 is usually seen as a poor coefficient of variance. The max work repetition being anything higher than repetition 2, really, the second repetition performed, and an inconsistent range of motion between tests as a hallmark that perhaps a more thorough familiarization period was needed, or perhaps more time taken with the trial repetitions was potentially needed. Finally then, let's move on to acceleration and deceleration time. I'll just change color for this. So acceleration time here and deceleration time, represented in milliseconds, is the time that it took the limb to go from a static position, i.e. not moving, to achieve the predetermined angular velocity. So in the case of this test, 360 degrees per second. Likewise, deceleration time is the time that it took the limb to go from the predetermined angular velocity to a static state. So much like time to peak torque, this is a measure of neuromuscular function, so the ability for the nervous system to recruit those muscle fibers and get the limb up to speed. Naturally, the lower the value that we see here, the better, the more rapidly that movement was achieved. It also highlights a rather interesting concept in that the term isokinetics, referring to a constant angular velocity, isn't strictly true. This is a bit of a side note, I suppose, but because you have to accelerate and decelerate, so whilst we consider a isokinetic test to be at a constant angular velocity, this period of acceleration and deceleration suggests that that isn't strictly true. Anyway, I digress. So there isn't much in the way of literature out there. So acceleration time is a hallmark of agonist limb function. So during extension, this is going to be the knee extensors, the quadriceps. During flexion, this is going to be the knee flexors, primarily the hamstrings, but also don't forget the gastrocnemius. That is a powerful knee flexor. We've spoken about this before when we talk about the agonist-antagonist and HQ ratio, the hamstring to quadriceps ratio. It should really be the hamstring and gastrocnemius to quadriceps ratio, but there we are. Really what we're looking for here, more so than anything, as I say, you may, at the time of recording this video, struggle to find too much published literature about acceleration or deceleration time, but really what we're looking for is symmetry between limbs, and of course between tests. So not necessarily between movements. So here we have on extension 80 milliseconds on both limbs, so that's good, there's nothing wrong there. However, during flexion, again we have 90 and 130, so a slight difference here, but again we're talking milliseconds, so it's again it's difficult to interpret. Deceleration time is more of a measurement of antagonist muscle function. So for example, during extension, if particularly at a higher angular velocity, this is going to be a measure of the eccentric function of the antagonist to slow the movement down. So how quickly we go from the pre-programmed angular velocity to a standstill, to no longer moving. In this case, this is going to give us some indication of how well the hamstrings are eccentrically functioning, and on this side we're going to have some indication of how the quadriceps are eccentrically functioning. Again, we take this with a pinch of salt, because even if we constantly move at a constant angular velocity throughout the test, and when we reach the end of the movement, obviously you can't go any further anyway because you've preset the range of motion. So it's not an amazing indicator of eccentric function of the antagonist, and we could just test that anyway by performing an eccentric test. So We're looking for symmetry between tests, we're looking for symmetry between limbs, but really I would make these very low priority in your report. If you do want to include them, really they're going to be of more relevance in higher angular velocity tests, so like the 360 degree per second test here, because this is going to give you an idea of that muscular recruitment during explosive movements. But again, I wouldn't place too much stock in them. Really, the purpose of this video is just to explain what these measurements are, more so than what you can do with them, because there isn't a huge amount. Anyway, I hope this has been useful, at least if you've watched them in order. And yeah, I will post more videos on this subject in the future, I'm sure.